Hello. Let's continue discussion on KL divergence. So the last time we saw what entropy is, and that is the average or expected surprise or information. We looked into what information is, that is given by the negative log of the probability of that event to happen. And then entropy is given by the expectation of information, that is in turn given by h of p, and this is for continuous random variables, this is for discrete random variables, and that is nothing but integral of p of x, that is a probability, and log of p of x. We also discussed that it could be also written like this, where this particular p is the one where we are getting the samples from, or where this part of the summation comes from, and this p is the one where we are calculating the information. So this is what we discussed about entropy. Now let's look into what also we can discuss one more thing about whenever we say we are trying to calculate some information, we also can say that we are trying to encode some information. Why we can say so? Because if we see, when we are calculating the log of this probability, and if we take the base 2, then we call it as bits, and if we just take the natural log, we call it as nats. And if at all, let's assume we want to calculate log of this number 8, what is it going to give us? It is simply going to give us that we want 4 bits to represent 8. As simple as that. We get this 1 in here to actually get this value of 4, but generally we just try to omit this one and just use this logarithm log to simply say that we need that many number of bits to encode the information that we have. And when we say log base 2, and when we talk in terms of natural log, we say the same thing, that the same thing can be said to have as nats. So we just keep in mind that we also sometimes say that while with entropy we try to say that the average number of bits or nats that we want to have for a particular probability distribution, to encode that distribution or to encode that information. Now let's come to cross entropy. So we saw that entropy is nothing but can be written as h p of p, where this is the one where we are getting the samples from, and this is where we are getting the informations. But now we have q in here. And what does this q? What is this q? This q simply says that we are trying to assume that this q is equal to p. So if we have data points, different data points, xi's actually coming from this true data distribution, but we don't know what p is. So we're trying to assume it to be q. So we can formulate q, we can give it some functional form, and then we'll be simply trying to calculate the information of these data points, but according to the distribution that we have assumed it, that is to be q. And that can be simply written as like this. We have the same formula, as in the first thing comes as the probability, and the second term comes as the one that we are calculating information from. So we can simply write it as expectation of the information coming if we use the distribution q, but the samples are actually coming from the two distribution, that is p. And this is what we know as cross entropy. And we have just simply written that samples are from p, but information is from q, assuming q to be p. And if you want to see, like, all the samples, likely samples are, we are getting it from this distribution. And then let's say if we have a sample x of I here being sampled from probability distribution p, we'll be calculating the information and using this value to put in here. And if we take the example of to build some more intuition, if we take the same example that we discussed, in which we had 4 different colored balls. So let's say this is P, and this is what? This is the actual distribution. So now if we have our old friend back in town, there is a curtain here. Now my friend is actually taking out balls according to this distribution, and according to this distribution, it has only blue. The cheat sheet that you are given is this one, Q. So now according to you, you would say, oh, is it orange? But here it is not. Orange is not even here, right? But according to you, blue is the most unlikely event that can happen. Or you'll assume that even if this is not there, this is just zero. So you would be surprised max if they say that, oh, I'm getting blue, because you won't be able to, you are not suspecting, as you're not uh, expecting the color to be blue in any case according to your distribution, right? So you're going to ask you're going to ask more and more number of hints to actually get to the actual answer that was there, the actual color that is there. To predict the actual color, you need more and more hints, right? And that's what we had an analogy, right? The in hints or information or number of questions that we are going to ask to actually predict the color of the ball. And this is how you're going to ask more and more questions, because you don't actually know the correct distribution. And if we want to have some mathematical formulation here, so let's say this is P, you are calculating the entropy, P comma P, summation of Px log Px, and then I am just putting all the values in here, and I can see that it is 1.36. And if I use, but the information that you are having is according to this distribution, right? So what I'm going to do is I'm calculating the cross entropy. So I'm using these values, P of X, right? So I'm using, for blue, it is 0.7. You can see that for blue, it is 0.7. For rest of them, it is 0.1, 0.1, and 0.1. But for log QX, I'm actually using these values, 0.25, 0.25, 0.25, and 0.25. And we can see that it is 2. And we can see that it is more than the actual number of optimal. So both are optimal, but in their own sense. So if we actually used P as our cheat sheet, then the total number of questions that we would have asked is just 1.36. This is the average number of questions, average number of bits to encode this information. Average number of bits to encode information if we use Q is 2. So we can say that, and this is the same thing that we can apply to our lives also. The lesser we know, the more we ask. Q is just an approximation of P, right? It is not actually equal to P. So we have less information about the actual distribution that is there. So we are going to ask more and more information. We need more and more information. We are assuming Q to be P. Less knowledge. So we have less knowledge about the actual distribution. But the more P and Q agree, right? So if we have a distribution, something like, okay, I can draw it here. I can draw it here, right? So if instead of this case, if I have something like this and this, so now it will be less, right? Because every time whenever P says that the likelihood is high, Q also says that, oh, the likelihood is higher. If we have something like this is just a hypothetical distribution of P and Q. But the more P and Q agree with each other, the lesser the cross entropy would be. And if they're equal, then what is going to be the case if they're equal? So H, P, Q, if they are equal, then it will become HP of P, and it will just be the equal to entropy, right? So more information is needed if Q does not match P, right? But till this point, we have got into this fact that cross entropy, more information. When Q does not match P. If Q matches P, then it is nothing but equal to the entropy of P. Then can we calculate how much more do we need? How much? If we say more, then how much more? So it is simple. We can just get the difference between two. Let's calculate the difference. This is the cross entropy, and this is the entropy. Cross entropy and entropy. Okay. So cross entropy is negative expectation of coming from P log of Q minus negative expectation of coming from K but log of P. And if we just rearrange the term, negative, negative plus coming in here, this coming in here, this actually coming in here. Take this is expectation under P. This is also expectation under P. Taking this common, log of P minus log of Q. Expectation of P under P, log of P by Q. This is just the log property of the log. And this is nothing but the KL divergence that we saw earlier. This is the expression of the KL divergence. So the KL divergence can be written like this. KL divergence can be written like this. KL divergence can be written like this. And this is the KL divergence is nothing but the extra bits or extra information or nats that we need if we assume Q to be equal to P. This is important, this extra. This is also known as the relative entropy. Why relative? Because first we are calculating HP of Q, and then we are having HP of P or simply H of P, and then we are calculating the difference. So this is also known as relative entropy. So this is the difference between the two distributions that we are having. What is the difference between two distributions? How different they are, how off they are. If they are equal, then our KL divergence would be equal to 0. If these two actually matches with, if Q matches P, then our KL divergence would be 0, because then in that case, we won't be requiring these this extra bit, right? So it will simply be requiring this 1.36 number of bits or information, or if we calculate in terms of nats. So in this case, our KL divergence would be 2 minus 1.36. This is a numeric value if we have actual distribution as P, and if we assume the distribution to be a uniform distribution of Q. So we have looked into the KL divergence and what is the intuition behind that. We have looked into what the formula for it is, how we have derived that. Next, we will try to, and KL divergence is always positive, and KL divergence of Q from P is not equal to P from Q. Like if we just switch these terms, it is not equal, it is not symmetrical. And we'll discuss more about this in the next discussion. Thank you.